Hold on. We'll test it. See if I do presenter, it doesn't.
Oh, I see, because they're both. Can we have a laptop up here?
We can. Yes. I have my laptop up if you like. You know what? Let me just.
What are you fighting? You're in CBR crazy. What are we, 3 universe? I'm gonna go sit down again. Unless you need me for anything. He's back here.
No clue. Might be Armand's.
No, I'm saying
That's how you spell Charlie.
There's no way to ask it, bro. I was getting upset.
Oh, I just shut that away.
I don't know.
I told him he doesn't want
Yeah, I just don't show how it is.
Yeah,
I mean, technically, I can do it. I think we have to. Yeah, it's like
yeah, the way they want to like talk out is Yeah.
Then you
One of the
excellent. Doesn't need rotations. No, you can't let
Yeah.
I know. Yeah, I kind of.
Everything is designed like the
It's actually
Have you done like that?
mechanical gas. I remember like she
Oh no, y'all.
Yeah, that's right. Oh, I did that.
something on YouTube.
You didn't.
Just like the views of what you have. They're very good at all of the totally look at this as
I think you can
just the paper.
How's it going?
Yeah.
I guess but like you're working. Suddenly end up. Just like the president, when you walk into it, or you might get a pencil.
Saving up. Saving
Maybe he was just here last week. The concept is like no, seriously.
I mean, then it's just
And then this one is kind of Armand, where are the labels for the Jimmy, I'm sorry. I made a mistake.
love you.
I love you. I understand.
I sound good. It's really not. As soon as you go in, everyone
I know, but
As I understand
Just get
Lower acceleration, but aggregate cost. Go cost very
I'm stealing my chocolate butter.
That's all right.
We're starting now?
responsible going fast.
Soon.
So that project and a bunch of yeah, people ask the question if it's a year one you're like, that's just that you didn't set yourself without us having too much. Yeah. We published our agriculture testing video. Like, you know, maybe right? Because they look where non-static here are all these things that we don't fit in those standards. And how we just like the guys from the aggregators come down and just putting up your calibration slide. You took note of it, calibrate the antennas, had it the same distance from the antenna inside the chamber, and to see the various different sounds and assume that you get them in, but you can point to you and say, this is for people who want the subject. Wait, we'll give it a minute. What's up?
I'm super happy.
Oh, did she come? Yeah. Oh, sweet. I didn't see her coming. Yeah.
Bro, she waved at me apparently, but I was too busy.
Oh. Yeah, fair. Oh, that's nice. Yeah.
Yeah, but she's probably gonna head off.
That's right.
For preventing airflow, because I don't know about the other side. I don't know about all the team members,
I'll do delivery. That's gonna call you.
Probably, yeah.
It's insane.
I gotta go. I gotta pay. Yeah. That's all right. That'll be at 7.
Yeah, just keep it on the clock. It'll be like
All right. All right. I think we'll get started. Hello, everyone. Hello. Thank you so much for everyone who made the trek out here to come and give us a little bit of feedback on our latest project. I guess, first of all, we're seeing some familiar faces, but also a lot of new faces here today. A bit of context. So Adept Rocketry Division is South Australia's only student rocketry team. So our mission is to give all of our students who are our members, we've got around 80 active members, some employability skills. So on top of the theory that they learn in university, we want to give them some practical skills when it comes to a full project life cycle. So we do that through rocket projects. We'll go into detail in terms of the different sub teams and things like that we have. I do want to first acknowledge all of our sponsors and supporters. Without any of these supporters, we wouldn't be able to do what we do. So we are completely a not-for-profit, and so we rely on industry supporters, not just for a monetary contribution to our projects, but also mentorship, expertise, free software, in-kind support. So thank you very much, especially to the NeoMech team, our newest sponsor. Thank you so much for coming down as well. Now, I guess I'll give you guys a little bit of context to the team. This year, we've expanded our leadership team a little bit just to reflect some of our learnings from previous years, especially in terms of accountability, project management. So we have myself and Arman here at the front. Do you hand up, Arman? So we are the directors of the Adept Rocketry Division. So we deal with a lot of the day-to-day activities in terms of finances, our project strategy, that sort of thing. I'm joined by Ujjwal, who is our Kronos team lead. So he's our rocket team lead. And so Uj leads our sub-team lead. So we've got Dimi. Do we have Dimi here? Yep, Dimi over there. He is our ground station lead. Hussein and Edward are avionics and electronics leads. We've got David and Ross, who are our documentation, compliance, and integration leads. Atman, who is our aerostructures lead, Liba, who is our payload lead, and Parsa, who is our flight systems lead. Now, each of those sub-teams make up our entire project in terms of the rocket itself, but also ground support and everything that goes inside it. So a little bit of an update since you guys last heard from us. So in 2025, we competed for the first time since 2019 in the Australian Universities Rocketry Challenge. We're pretty proud of our performance. We came 4th place in 2 categories. So the rocket that you see behind me and the rocket at the front. So we got Project Myriad and Project Lightning. They were our 2 entries into the competition. Both categories, we came 4th place. I should note, we were coming 2nd place up until launch. So the reason I say that is it reflects our team's capability, and the one part that is particularly resource intensive in terms of investment into actually building the rockets. That part we're still learning, we're still improving. We also walked away with the Lockheed Martin Technical Excellence Award. Again, really speaking to our team's technical capability in presenting their work and being able to talk about what they're doing, and also following engineering industry standard practices and processes. Since then as well, we've grown, we've doubled in size. So from around 40 active members, we now have 80 active members. And our big focus this year is focusing on formalized engineering processes. So taking our learnings from last year, all of the little intricacies and running a large scale project, figuring out how we can improve those, and allowing our team to walk away with real engineering sort of processes and documentation and simulation and analysis skills, rather than just saying, yep, we're building a rocket, it's a tube, it's got a nose cone, let's launch it. So we want our team to really have that employability behind it. So some of the photos here you'll see are Project Myriad in action. And yeah, very, very happy team. Now, our goal for AUST 2026 is to win. So we want to come podium finish. We want our passion, our drive, our ability to come through. We're competing, the competition itself has doubled in size. So we are now competing, it's not just Australian universities, there are universities from across the world, from Thailand, New Zealand, that are also competing. And we want our team, our Adelaide University team, to show just how capable we are. I'll now hand over to Uj to talk a little bit about our design approach and traceability. Before that, just a little bit of a note on today's format. So I like to really tell everyone who's here, not just our supporters, but also our members as well who are sitting here, this is an opportunity for us to learn. And so what we want is everyone to be as critical as possible, ask as many questions, really grill our team, so that any sort of design decision that we've made, either we can justify it or you're asking us the relevant questions that maybe we need to make changes. So what we'll do is every team has around 15 minutes to present their work. After that 15 minutes, we will open up a 15-minute question time, and that's the opportunity for everyone to grill us. And then from there, we'll move on to the next team. So we will have an intermission at around 7 o'clock as well. There'll be some food and refreshments and an opportunity to network with our team. But yeah, thank you so much for coming. I'll now hand over to Uj.
Thank you so much. Hello, everyone. Like Sia said, my name is Uj, and I'm the project lead for Project Kronos. I'd like to walk you guys through our design approach and how we've learned to fix it from last year. So the one thing that we really struggled with last year was having traceability and keeping our documentation up to par. So we're mainly focusing on having everything combined on Notion so that it's easily accessible for everyone, and any sub-team can look at any other sub-team's work and easily understand what's going on. We're also planning on keeping our testing at a higher level than last year. That means we want to flight test some of our subsystems like the flight computer, which avionics will talk about more, on our L2 rockets, and mainly focus on design iterations, as Project Kronos is a derivative design of Myriad. So the scope of this year is to reach exactly 10,000 feet AGL with a novel scientific payload. This will also have an SRIDE flight computer with live telemetry. We're also focusing on an active apogee control by air brakes, and for the first time in ARD history, we're trying to do a SRIDE pneumatic recovery. So the goals, obviously, this year are to reach a podium finish, and mainly to refine and advance our capabilities in manufacturing, testing, systems engineering and planning, documentation, and the engineering process. This year is mainly a foundation for future years, where we plan to go to international competitions like Spaceport America. So introducing Project Kronos. As you can probably see, the main geometry and dimensioning is very similar to Myriad from last year, but we are planning on adding a boat tail, a metal nose cone tip, a different fin shape to get us to that extra apogee. Yeah. And now I'll move on to the subsystem review. So aerostructures this year is mainly focused on implementing industry-standard manufacturing techniques. Flight systems, which encompasses our air brakes and recovery, are working on developing a working altitude control, and recovery is working on making an SRIDE pneumatic recovery. Avionics is working on, sorry.
Quick question on terminology. SRAT?
Oh, sorry. Student Research and Development.
Thank you.
Avionics is working on a student research and developed flight computer. Ground Stations is working on a live telemetry capabilities, which are new to this year. And Payload is also working on a SRAD scientific payload, which is being developed in-house for the first time. Now I'll hand over to Aerostructures. Oh, sorry, Condoms. So just to walk through the concept of operations. So generally in the AURC 10,000 feet category, we take our rocket to the launch pad and activate the avionics. This installs the igniter to the motor, and once continuity is checked, the motor ignites and the rocket launches. When the rocket reaches an appropriate altitude where our flight computer thinks it's viable to deploy the air brakes deploy and make sure that we reach exactly 10,000 feet. At apogee, the drogue chute deploys, streamlining the descent of the rocket, and then at 1,200 feet, the main chute deploys. After that, touchdown and recovery occur, which is a big part of AURC, where we need to recover the rocket fully intact. As you can see, the red dotted line represents where we are right now. We've passed the detailed design section of our timeline, and we are moving towards manufacturing. That's where advice from you guys comes in, where we refine all our techniques and hope to make a winning rocket. Now I'll hand over to Aerostructures.
So guys, I'm Aban, the team lead for Aerostructures, and I've got Urvi and Noah next to me, who are members. So for Aerostructures, we started off with the system requirements from AURC, which are our external system requirements. This would include some safety stuff that they want, such as like the touchdown speed, velocity, the rail departure velocity, the aerodynamic stability margin for the rocket, and the mechanical safety factor they expect us to use. We also have internal system requirements, such as the internal diameter, the motor class that we're using. These are mainly due to us reiterating on the design from Myriad, and this will allow the other subsystems to start their design process earlier on due to like some consistency between Myriad and Kronos. We're trying to reach a simulated altitude of 11,000 feet due to an error with Myriad's performance. For Myriad, we had a simulated altitude of 10,000 feet, and then Myriad undershot this value. Therefore, if we overshoot it, we'll be able to use air brakes to lower this apogee value to the exact value we want. We also have a different internal architecture with avionics and flight systems. For Myriad, I might just come around to show you guys. There were separation points here, and I think it was here. So a parachute would release from this end, and a parachute would release from this end. In technical terminology, you would call this dual separation, dual deployment recovery systems. But we've transferred from that to a single separation, dual recovery system, dual deploy system. So that means we only have one coupler that opens up to release the parachutes, and both the parachutes exit from this one open tube. So if we have a look at the system overview, I've just got a few dimensions that are constraints for the subsystems to adhere to. This allows us to package the rocket before we start going into the manufacturing phase, and this is supposed to be like a largest value you can go to. So they can optimize it further, and we can get the rocket down to be shorter. But yeah, we also have a boat tail for this year, which is supposed to be reducing the low pressure drag from the end of the rocket. For the flight profile, when we launch, the rocket motor ignites. This gets us to apogee. At apogee, we have the separation event with the coupler system, and a drogue parachute is released. A drogue parachute is basically just a parachute which is smaller. Therefore, it reduces drag, but not to such an extreme position where the rocket can fly away further from the launch pad. Then at a certain altitude, we also deploy a main parachute. We deployed the main parachute. This main parachute is supposed to be increasing the drag overall, so it lands at the certain velocity that we require.
So in terms of manufacturing, we've come up with distinctive methods for each part of the rocket. For the nose cone, we'll be 3D printing a split mold that will be sanded and waxed from the inside to make sure it's smooth. Then the female component of the mold will be fiberglass, and that will be a separate layer, and then epoxy will be added on. So there's 2 separate layers for it. The male part will then be added on with a vacuum bag to make sure there's no air bubbles left or any voids. For the aluminium nose cone tip, we're going with a CNC lathe method, where a CAD model that best meets our mass requirements will be created first. Once that's been created, a threaded male spigot will be added to the design so that the tip can be screwed onto the bulkhead using Loctite. For the couplers, we're going with the fiberglass layer, which basically is just layering fiberglass with epoxy over the coupler mandrel. The reason we went with this method is because the couplers are not in direct contact with the air, there's not really a need for them to be manufactured with as high of a precision as some of the other rocket parts, such as the body tube. And as we've mentioned multiple times, we have a boat tail this year, which is a new incorporation. For that, the method we're using is vacuum bagging a fiberglass part in a split mold. So we utilize a split mold and a tabular vacuum bag that will be pressed against the internal surface of it. Now, with the body tube, we are going with the hand layer, the same that we use for Myriad. However, we have reduced the wall thickness this year. So Myriad has a wall thickness of 5 mm. This year, we're going with a 3 mm thickness. But the construction method is still the same. So Mylar will be applied to the mandrel surface, which will act as a release for the finished tube to separate more cleanly. Following that, fiberglass will be laid over the top of the mandrel and wetted with epoxy using a brush. Once this layup has been completed, peel ply will be applied. Now, a major difference is how we're constructing the mandrel itself this year. We will be beginning with a PVC pipe that will act as a placeholder. We'll apply a Mylar inside to make sure it's smooth. Following that, one side will be sealed and the other side will have expanding foam that will be poured into it and around it. This will create a mold for the mandrel. Once this has cured, we'll be removing the placeholder, so we're left with a foam mandrel. And this will be prepped for the fiberglass layer afterwards. Now, fins are one of our major differences from Myriad this year. We're going with trapezoidally swept back fins. And we have 2 iteration stages that you can see up there. We originally decided to go with an aluminium honeycomb core structure, which will have either an MDF or plywood frame that will be tip-to-tip reinforced. But a major issue with this is that aluminium honeycomb is extremely hard to shape and bond. So this increased the chances of manufacturing inconsistencies in our design, which we obviously do not want. So as an alternative, we came up with Millimax, which still has the honeycomb structure, but it's a lot easier to shape and bond as compared to aluminium. It also has better vibration damping, which helps with the fin flutter. Moving on to centering rings, we'll be using MDF sheets that will be laser cut to our design. And finally, for the bulkhead, we'll be going with CNC routing. So a CAD model that includes all the through holes, all the U-bolts, avionics wiring, recovery harnesses, and everything will be CAD'd up. Once that's been done, we'll be using aluminium 6061 to manufacture the bulkheads. Now, in terms of how we're interfacing with the other subsystems, so to be able to actually confirm our method of interfacing, we need confirmed dimensions and clearances from everybody. We need mounting requirements and interface and connection details. So once that's been finalized within all the other subsystems, we will finalize our method of interfacing. Now, finally, the major differences from Myriad to Kronos this year. As I've mentioned, we've reduced the wall thickness from 5 mm to 3 mm. We've had other rocketry teams that have used a much thinner wall and still have succeeded in it, so we're hoping that works for us too. The fin shape and material, so as I've mentioned, we're going with swept back trapezoidal fins this year with a honeycomb structure. And again, we have a boat tail. In terms of manufacturing, we're introducing vacuum bagging, which we haven't done previously, so that's something exciting. And you would have noticed in our open rocket file that some of the parts are rearranged. This is because as we're going with single separation deployment, our parachutes have to be adjacent to each other. Therefore, the avionics bay and air brakes have had to move aft.
For simulation work, we're going to be using ANSYS as the major package with fluent and mechanical and composite pre-post. For the ANSYS fluent campaign we're running, it'll mainly be focusing on the camera mount because we will have an internal camera pointing towards the air brakes. This will allow us to see how the air brakes is functioning during like the input versus the output itself. We'll also be looking at the airflow from the camera mount due to the flow and how that affects the air brake system as well. For the boat tail, of course, we need to check how effective the boat tail is in reducing the low pressure zone behind the rocket. And we'll also be investigating how air side slip affects the stability of the rocket. For the mechanical and the composite pre-post campaign, we'll be running a surface stress comparison using the CFD model to simulate the surface flow. Then we'll also be looking at how the internal mounting solutions per subsystem affects the overall stress on the airframe monocoque. We'll also be verifying all the mechanical processes through testing.
Right, so for physical testing of the rocket, there's 4 main components we're going to be testing. So the aluminium tip on the nose cone, the internal bulkheads throughout the rocket, the fins, and the airframe couplers. So for the nose cone tip, we are going to be doing tensile testing just to make sure that the forces that we experience during the flight and separation with inertia, that we can actually handle them based on the adhesion that we apply to it. In terms of the bulkheads, we'll be doing compressive testing internally to make sure that the actual force from the motor doesn't affect and actually maintains its position in the rocket. And then also importantly, tensile testing on the bulkhead near the nose cone, because during separation, we want to make sure that the actual bulkhead maintains its position during the force that we will be experiencing during that separation. Now, for the fins, we're going to be running cantilever testing to make sure they can handle the forces we're expected to experience during the flight. And the airframe couplers, we're going to be running both compression and tensile testing to make sure that during the flight, when it's going up, the compressive force, we can actually maintain that. And also during separation, we will not be worried about the tensile forces there either.
A few project risks for the sub-team are just manufacturing complexities causing time delays. This can be mitigated through using smaller scale manufacturing initially to iron out all the manufacturing processes. Then we also have an integration challenge with the sub-teams due to just time, basically. But we'll be starting discussions after the CDR is concluded, and this will allow us to hand in hand design everything possible so integration is as quick as possible. A decent risk for us is components failing during testing. This will be a good and a bad thing, because we know the component doesn't work. So we do have backup manufacturing techniques which should yield a higher strength component, but these also, we need to weigh up the price and the performance of the components as well. Here's a quick rundown of the project milestones that we're looking at. So once we implement the feedback from you guys, we'll be reaching out to the subsystems to start the integration and mounting solutions that we're looking at internally. Then we'll start manufacturing the process validation stuff. Then we'll create the simulation model. And then we're looking to finish manufacturing while the simulation is going on. Then we'll be having a final full team integration period according to project timelines. A quick budget overview. Yeah, majority of the pricing is just on materials such as fiberglass and epoxy. A new category for within the budget is vacuum bagging infrastructure due to us not really having that right now, and also the consumables that go alongside it. However, the manual making process seems to be fairly cheap for us right now. To measure performance within aerostructures, it's pretty simple, I think. Basically, we need to meet system requirements like all good engineers. We need to make sure that the integration side of things go as smoothly as possible. We need to establish a good manufacturing capabilities. We need to establish good manufacturing capabilities that we can pass on to the next year and let's say ongoing years. And then as ARD is a student-led team, education is always a goal of ours with transferring knowledge to them, to newer members, I mean, and exposure to engineering experiences not found at university courses. Questions?
So we're going to be sticking to a strict 15 minutes per starting, but if you don't get questions in, you can do so in the break or after the CJ. So any questions?
If you just run through the decision, we're going from 5 millimeters to 3 millimeters on the body.
Yeah, so when we were researching a lot of the airframes that other teams use, especially in Airport America, a lot of them were running either 3 millimeter airframes or 2.5 millimeter airframes. So we're trying to see how effective that would be with our current manufacturing technique and seeing if we can refine it further to get the necessary strengths we're looking for.
What's the advantage going to that? You get more aptitude for things like that.
Yeah, so basically a simplistic way of dealing. I mean, you can if you want.
So the safety factor on the 5 mil is a lot higher than it needs to be. So adding a lot more weight. The issue last year obviously was that we didn't reach altitude to begin with. So
And that was due to weight, you think, rather than a difference in the thrust of the motor.
So the thrust in the motor hasn't changed.
Okay, so that's fixed.
Yes. So as the motor is a fixed parameter, the most appropriate things to change is then the weight of the overall item. So we've reduced the overall thickness because we have that we have the flexibility in the safety factor that was originally applied.
Okay, so the failure to meet altitude last year was due to your simulation not replicating the maximum thrust you had. Possibly. I just wondered if you found that.
Yeah, so it's kind of hard to verify that again because we would probably need to relaunch the rocket consistently. That also costs a lot. But I'm pretty sure the project was plagued with just like small tolerance issues, not tolerance issues, but small issues just snowballing later into the project, such as the airframe being heavier than it needs to be, the environmental conditions compared to the simulation versus Wycliffe's where we're launching at. And yeah, it's because we were, if I remember correctly, around like 1,000 or 1,200 feet off, right, Sam?
So we were aiming for 10,000 feet. Our simulations said around 10,500. We got 8,900. And one of the things we attribute that to is our just lack of experience in manufacturing, and we believe reducing the wall thickness is an easy way to reduce the weight and make it more efficient.
Okay, so my only concern is that the variations you have in the different elements that force you to be, so that's more than 10% reduction. How do you know that going to a thinner motor design, apart from the safety thing, doesn't create other uncertainties, make it less stiff in terms of mounting the bulkhead and the coupling, and it increases rather than decreases the uncertainty of the higher altitude?
Yeah, it's more. Do you have an answer for this?
Yes, that's what I was testing.
Yeah.
It's yes, it's the
Yeah.
short answer. So obviously, part of the simulation campaign will also be to optimize the bulkhead design. So we'll be saving weight wherever possible. I am keenly aware that the primary issue with last year is mostly surrounds the overall weight, and this is an issue that we'll be dealing with this year. Using honeycomb Nomex fins is part of the solution. Doing optimized bulkhead design is also part of it, as well as obviously the thinner airframe. So as with small savings across the board and high fidelity simulations, I'm relatively confident that we will be able to at least more accurately demonstrate what we expect, because we also we want to overshoot so that we can get the airbags deployed, as that was not a factor it didn't work last year.
Final follow-on question: do you have two different simulators? Or you just use the rocket?
So OpenRocket is the main simulation currently, and then we'll be transferring over to ANSYS packages just to establish a center of pressure, and then that way we can. Does that kind of answer your question, or not really?
Well, there are other launch simulators.
Yeah, there is a RAS error that I'm aware of.
It doesn't take much to run the model again in simulators to get similar answers. With OpenRocket, it's not perfect.
Yes, so
at least it'll give you a range of just one number that you think.
yeah, we do need to implement RAS arrow in our simulation process as well. But the biggest factor for not using that right now is showing the actual system versus the complexity that you can get. Like in OpenRocket, we can model up a more complex system just because we're familiar with it. We've used it quite a lot. And then when we do have time, basically the biggest factor right now, we can transfer the OpenRocket model into RAS arrow, and we need to familiarize ourselves with how the parachutes are deployed and stuff, just to make sure our key requirements are here. Because OpenRocket does a pretty good job in estimating the altitude or the apogee we reach. However, for when compressibility matters, which for this project it will, RAS arrow is a better simulation, and we'll probably do that in a bit. Yeah.
Thanks, guys. Good work. So, although you're the aerostructures team, you're also responsible for the trajectory analysis. Is that correct?
Yeah.
Okay. So, you showed one trajectory. It looks like it's just one run.
It was just a finalized run that we had. Okay,
so what did you do in terms of evaluating the dispersions of things, in particular wing? Because there's parameters of the vehicle that are perfectly known, like the drag and perhaps even the mass. The wind is going to be quite variable. So how do you take that into account in this 11,000 foot estimate?
Later in the presentation, Ground Station will be presenting a part of the work that Ground Station is doing is developing what's being referred to as a flight envelope model, which will take in local the local weather station data from Wycliffe's to attempt to do that modeling. As of now, we don't have that. We haven't done any pre-flight. Yes.
So sort of general engineering approach when you've got this major source of uncertainty is to, have a few different scenarios or many different scenarios, multi-color simulation. And so then you might set a requirement and say, okay, under 95% of the expected cases, we need to reach at least 11,000 feet. Is that the approach you're taking, or is 11,000 feet like the average expected performance, in which case you've got a high chance of dispersion being below that?
For the environmental factors, OpenRocket doesn't really have like a high range of variability that we can do. We can have like the wind speed data being injected into the simulation, and then a few like barometric values, if I remember correctly, but it doesn't really represent the current environment that we know white cliffs to have. So
the point is, I'll move on in a second, but the point is just do a bunch of different wind scenarios.
Yeah, and create a flight. Yeah.
It is possible.
I'm going to change focus. Another question. So just going back to the the 5 millimeter, 3 millimeter reduction. So you've talked about other rockets successfully working with 3 millimeters. So you've got your own manufacturing techniques and materials and everything, and a low distribution within the rocket. So what are you doing to have confidence that you won't have a structural failure in this new rocket body design?
Yeah, so we're also using a new method for fastening couplers and stuff.
Okay, so this just focus on the power field, so it's not just the joints, but in the body, in the tube itself.
Yeah, I meant the subsystems, not the couplers. That's a mistake on my part. But for Myriad, we were using a lot of pins in shear forces, but right now we're transferring to.
Okay, so I'm not talking about joints or interfaces. I'm just
talking about the overall A-frame.
So this is going to be in compression.
Yeah.
Due to the acceleration of the force on those kind of hand bending from wind loads. So there's going to be a critical point along that tube for compression.
Yeah.
Composites aren't great in compression. What's your margin of safety? How have you calculated that?
Yeah. So the compression testing that the coupler will receive, it'll be the same material and basically the same manufacturing process that the airframe will receive. So we can interpolate those data points into how the airframe would be affected as well.
And so how do you account for bending in the worst case testing environment?
Also the length of your column, any buckling.
You answered my question, but that's a good question.
In addition to the testing that we'll be doing, we're also going to run FEA and CDF analysis on the parts that CFD analysis on the parts that we think are likely to buckle or have a stress factor that's not good for our rocket. So once we've, like we said, after today's presentations, we'll be finalizing what each subsystem requires and how much we need to incorporate in our FEA analysis that the body tube needs to be able to hold.
Okay.
So
one comment before So in these compression tests, you typically account for the bending effect as an overflux. You're familiar with that term? Yeah. So that would be you increase the compression load because that's an axial test. So there should be an overflux factor. That's all.
Thank you.
Basically, that was my one up in my FEA, no worries. One of my questions was you mentioned that weight reduction is an important part. What is that why fiberglass over carbon fiber? Is it a difficulty manufacturing side of things? Why did you choose the composites that you did?
All right, so I'll just mention about the fins because we researched mainly about the fins. The reason for using honeycomb structure is to get a weight to strength ratio to be really high. So as we know, honeycomb is a very light structure. So and it's got quite the stiffness that is required for our rocket, and tip-to-tip reinforcing it makes it stronger. So our first goal was to reduce the weight. So we did that with the material that we used. And to make sure that it's stiff enough, we're going to do tip-to-tip reinforcement. And then, as we said, we'll be testing it as well. So in terms of weight reduction for the fins, that's how we went about it. The other parts I can get to.
Yeah, so the material choice for the majority of the airframe is mainly due to avionics needing transmission linked with a ground station. So if we do have carbon fiber parts, that'll create a loop if I'm pretty sure.
It's the dielectric constant that's
Yeah.
the issue.
Your Faraday cage sort of thing. Yeah.
Yeah.
So the manufacturing techniques at the moment aren't at a sufficient level of maturity where the entire item could be carbon fiber. So as featured on Myriad, where possible, carbon fiber reinforcement will be used. But it mostly comes down to issues with.
Yeah. Another point, honeycomb is very stiff for its thickness. Basically, to get to sheet length with an I-beam, it does have a non-zero thickness. And from memory, I haven't spent a lot of time recently playing around with Open Rocket, but when you're putting together your actual structural side of things, your thickness dimension is often a pain to get right. And at the speed you're talking about, that added thickness will add up quite a bunch. Have you incorporated that into your model? Have you added extra thickness? Have you added extra sail area? What are we talking?
So basically, with the fins, if it gets thicker than we anticipate, that's why we've kept a backup of vacuum bagging. But vacuum bagging, obviously, on fins is quite difficult, and this is the first time we're actually introducing vacuum bagging.
Right. Vacuum bagging, that meant the fins thinner or pointier or
Compress them a little bit. So once they're vacuum bagged, we can shape them again. But the vacuum bagging part is the difficult manufacturing technique that we haven't tried on fins before. So yeah.
The side effect of vacuum bagging on honeycomb obviously is the risk that you fill the comb with resin, which is sort of exactly what you're trying to avoid.
Yeah.
There are methods around that can be used to prevent that. As far as thickness of the fins will be an issue, yes. I can almost guarantee that. The question will be which thickness is best. So in the testing that's going to be done, we're going to make 5.
This one.
Where
do you want to go?
Just go to the.
Next.
That's fine. We're going to make 5. So we're going to make one of an alternative thickness just to see how it performs. If it's a case of we are above the non-zero element, which I'm expecting that we will with Nomex. If this was aluminium, I would entirely agree, having dealt with that in the past with automotive components. So we'll see how that performs, and if it goes fine, then we'll change. We'll adjust our minimum diameter. Sorry, our minimum thickness.
Thank you.
Here's a quick question. Do you guys have an idea of how much weight you're going to save?
This will most likely be like after the manufacturing run's been done, because we haven't estimated that. Not really, just because internal sub-teams also need their weight budgets to be calculated and then accounted for.
I'm curious, why did you seem like you simulated an altitude beyond where you need to get to? Can you explain to me why you do that?
Beyond, as in the air brakes. So the intent is for the air brakes to be used. And this will be explained later how specifically that works. But essentially, it's we've intentionally over-projected our altitude so that the drag we can rely on drag to get us to that spot. This has been used quite a few times in the past.
That's not new. That was used last year.
Yes, the difference is that they didn't reach altitude in the beginning, so the margin for those flaps to deploy was too low, so it didn't work.
Right.
So this use, that's why we've added that extra margin. All right.
Next up, we've got parser for flight systems.
Yeah. Evening, everyone. My name is Parsa. I'm the Flight Systems Lead for this year's Kronos project, and I'm here with Propellant and Stefan from our recovery subsystem, and Alex and Charlie from our air brake subsystem. To begin with, I will give a quick review of what is Flight Systems. Flight Systems is responsible for deployment, integration, and testing of our air brakes and recovery system that ensures controlled flight performance, hitting the 10,000 apogee AGL apogee and our safe recovery. I will hand now to Alex to explain our software side of our air brake system.
Great, thank you. So our when we launch the rocket, obviously we have a lot of variables which we can't account for. You've got low and high pressure of air, you've got pockets of wind, you've got mass variability, and that all leads to quite a large apogee variation. So that's something we can't control before we launch the rocket. So to tackle that, we're going to use an air brake system, which is where we have an onboard computer, which takes a variety of variables into consideration, and will deploy fins mid-flight to spend that excess energy that we have because we overspec the rocket to go higher than the 10,000 feet target. So to tackle this from a software perspective, we're building a predictive system, not a reactive system, so not a PID system where we're looking forward and predicting how high we think we're going to go, and then making choices depending on that. So we've got the gather data, process and predict phase, and action phase. A lot of it is built on, we get our current position and our current situation that the rocket is in. Hopefully we'll be projected to go higher than our target. And then we do a lot of calculation to figure out the amount of force in drag that we need to apply to lower that to where we want to be, which is our target. And then we use a table, which we derive using CFD simulations, to determine the amount of force and therefore the amount of deployment required from the air brake tabs. So this is a loop which we're going to be running on board, hopefully 10 to 100 times a second. So we should be able to correct for very small differences in the environment, and we should be able to stay on top of our goal. So the mechanical implementation, we're using a radial cam track mechanism, which has a rotating disc with curved slots, and it's pushing the air brake tabs out, which have pins. So the path of that curve has specifically been designed to deliver a linear relationship between the servo angle, which drives the mechanism, and the tab deployment. So this reduces firmware complexity, gives us one less place where errors can occur. Pastor's got the demonstration there. So it also guarantees that equal deployment of all 4 tabs at once. So we're not going to have any lopsidedness, we're not going to cause any spinning or any offset, we'll pass it around. Because we have one single motor input, and as long as nothing jams, everything should be deployed equally. This attribute and the simplicity of the design, it will be easier to turn than that, is why we chose it over alternatives like a 3-bar linkage system. So that's the air brake mechanism and software. I'm going to hand it over to Parsa for the
One thing that we did with Project Kronos is to look up our 2 previous experiences in air brakes, which was Project Lightning and also Project Myriad, and derive all of the best things out of it pretty much. So one thing that Project Lightning had over Project Kronos was having its own outer aerostructure, which we're doing like so here. So the air brake system will have its own housing that has an outer diameter of 156 mils,
And with a full deployment, this diameter is changed to 216 mils, providing us with 30 mils of full deployment after tabs, which compared to last year, it's close to 150 times more deployment. The coupler section is mounted to, so the airframe of the airbricks is mounted to the coupler section at a 45-degree angle to connection bolts and to reduce the vehicle drag, so the rocket's drag, as a 0-degree angle would introduce extra pins outside of the rocket. So the couplers are going to be manufactured using fiberglass, and the thread inserts for them are going to be placed and then epoxied into. The housing itself is going to be made out of aluminium 6061. I will then now hand to Charlie to explain our safety mechanism.
Right, so AURC requirements dictate that we need to have some kind of mechanism for the air brakes to retract in case of a power loss failure. We had two primary ways to go about this in an electrical backup using a capacitor and a mechanical backup. We've chosen to go for the mechanical backup because it is more comprehensive. It deals with a broader range of failure modes such as controller board failure and the servo wires becoming disconnected. However, due to the limitations in our servo motor, we needed a system which did not fight the servo motor during standard operation. So if you go to the next slide, we are using a locking mechanism with a normally open solenoid, which will keep these sliders, which retract the air brake pins away from the areas where the air brake pins will be during standard operation. Should power be lost in whatever way, or the controller board fail, the solenoid will lose power and that pin will retract from the holes in the sliders, and they will retract under the linear spring tension, pushing the air brakes in.
We'll now move into recovery side. A brief overview of recovery itself. So recovery refers to safety landing of our rocket using a drogue chute, that's a smaller chute, just to give guidance to the rocket and reduce the drag to some extent, and then a bigger chute that is set to be deployed at 1200 feet. Parachute deployment happens by a forceful separation of the body itself, that we are traditionally using black powder, but now exploring gas options, hence our pneumatic device. I will then hand to Propellant to explain further on this.
So some of the reasons why we're choosing a pneumatic deployment system over a black powder system is mostly because of safety concerns. And although some of the pros of black powder is that you can measure the exact amount you need, whereas for the canisters, we have to buy default amounts since we're buying the canisters just from the store. And then also testing under university guidelines, the canister is so much easier to do than black powder. The university are very difficult about testing black powder. And also black powder ends up charring and causing some damage to the internals of the rocket, and the pneumatic should not. But we haven't done this before, so that is why we want some help in deciding which one we should do. So once the rocket reaches apogee, it'll hit the first stage, which is our design. We are picking between an E-match with a little bit of pyro, and that is pretty much the same as the redundancy one here that we just buy the COTS version. However, because and they'll explain further later, but the canister 38 grams isn't enough to separate the rockets. So we're designing one with 45 grams. And if that's not enough, a 74-gram canister. And then the second one is using a DC motor to release pretty much a spring, and then the DC motor will turn a latch that will release the pin, piercing it. And then finally, to deploy the main chute, we have this TD2 tether and release device. There's a little video later, but an E-match pretty much releases that, and that will release the main chute. So this is where the arrows are pointing will be where the COTS and SRAD will be. So these are the canisters, and then it pisses up this way, and that is the TD2 tether release device. So I might just quickly play the video. I just already cut it. So you can see how that releases. Yeah, so just an E-match, and it will just release in the middle there. And then this one will show just kind of, that's an 8-gram cartridge there, and that's how much force it kind of provides on a piece of thick wood. This is our assembly diagram. I've just put that up there. So the green thing there is the tether release device. The parachutes are packed, and then we have, after the CO2 releases, there's a drogue, that's the drogue deployment, the small parachute deployment, and then the main one will happen after.
I will further expand on this a bit more on the prototype that we've got at the front. So as you can see, this is the main bulkhead that we use, and the red option is the commercially off the shelf, so COTS option that we purchased, and the grey one is the one that we are planning on making our own, that our SRAD version. So at Apogee, where we've got drogue deployment, we will have either of those deploying our coupler outwards, and then which the drogue is connected to our main eyeballs. Once so, the main parachute itself, the carabiner for it is connected to the tether release device that is also connected to the main eyeball. So once this device is released, it will enable our chute, the main chute, to deploy.
Just see the ground bit there.
Now the options that we've got for our SRAD pneumatic design is either a DC pneumatic or a similar system as the one that we purchased. So the DC pneumatic has a preloaded spring placed right over there, but is then open with a DC motor connected to a latch that enables the pin to pierce through our CO2 canister and enable the gas to come out. I'll hand to Stefan to explain the pyro option.
So the pyro works pretty similar to that one. Essentially, a charge come at the bottom, it's going to hold about 0.3 grams of the pyro charge. Then ignited by an E-match, push the pin forward, and that will pierce the 45 gram CO2 canister. So we're also buying these canisters, we're not making them. And then we'll have a compression spring which sits between the pin and the CO2 canister, which will retract it, and the air's forced out of those holes on our casing. So we're opting to go with aluminium 6061, the outer casing of the charge cup, since it's lightweight, has a high strength to weight ratio, and also high machinability. You can see the table here, different size CO2 cartridges and how much volume they eject. So we've opted to go with the 45 gram one. As we said before, 38 grams is not enough. So that's what comes up.
This is a testing procedure diagram. I won't run you through it completely, but pretty much for the SRAD, we're going to pop test it with a 45 gram canister, and if it does work, then great. If not, we'll use a 74 one. And then pop testing for COTS. We're going to use a 38 gram canister, just like as you saw it before. If it works, amazing, but obviously we predicted that it wouldn't. So the other option was to use like an MDF disc to minimize the volume. So it'll go right before the parachute area. So kind of just on the right side of the big parachute there, that's where the disc will sit. And so using the 38 gram COTS canister should be able to create enough pressure in a smaller volume to push the parachutes out. But the issue with that was, and then whether or not we needed an O-ring for that, but that's just a matter of friction. But if it didn't work, the issue was that we couldn't, our SRAD CO2 canister might be too powerful to be using in a smaller volume. So it's kind of a testing process, and if anyone had any extra commentary on that would be good.
As of our risk and mitigations, so I'll start with air risk itself. So failure to deploy is we aim to test on that by ground testing and sample validation. The other one can be over deployment, that our state gated logic limit this. We can have mechanical jams that we aim to prevent with correct tolerancing and deployment testing. But the most important one is the power loss that we've further explained, that we prevent using our mechanical safety mechanism. For our recovery, parachute deployment failure, hence having a redundant commercially off-the-shelf option, and a section separation failure. That is the reason that we do pop testing, so ground testing before flight. And we may have electronic failure, but we do have redundant electronics available that avionics will further explain on this. As of our project timelines and milestones, we are sitting on CDR, and our manufacturing starts 1st of July, and aimed to be 1st of June, aimed to be finalized and finished early July, mid-July, and the rest would be our testing procedures in action. Questions? Oh.
So are you guys doing anything to prevent jamming when there is the force of the air that's bending your input?
Yeah, so for us to prevent this, as you see on the design itself, we have taken this into consideration. One way is we calculate the forces when we were doing our initial calculations. So we have, according to our simulations from last year, close to 50, maximum 50 newtons of force applied on all 4 airbrake tabs. Hence, by knowing this difference, we reverse engineer the static coefficient of friction that we need to have in between our aluminium plates and tab system, and also our bottom holders that I like to call, which is 0.4 as a coefficient, choosing SLA printing, resin printing as our base. That prevents us a lot, this jam from happening. And also the design itself utilizes ball bearings that uses these the friction in between the pins holding the movement track in place, preventing this action.
Thank you.
Are all of your mounting is 3D printed for the ZO2 containers? Is there any risk of the containers disconnecting? They seem to be connected just at the thread. What are the shears?
Our mountings for our SRAD pneumatic, they're all aluminium 606 watt.
It won't be 3D printed. This is just a
the design that we've got is just for the show. It's a 1-to-1 scale of prototype of it. So all of our design at the moment, except for the piece itself, the pin is aluminium 6061, and the pin is
going to be steel, or like a light steel, because the aluminium is going to be too soft for when the canister gets pierced. The pressure might ruin the tip, and it just wouldn't be a reusable system.
So when you're going at high velocity, you're going to, of course, have a different amount of static and dynamic pressure as you're zooming along. No doubt you've got some way of, you've got some way of equalizing pressures as you're heading up to altitude. While you're heading up, though, have you looked at how much force would be required to have the internal pressure just up out the air brakes? Is the opposite to, do you have too much friction and it jams? Do you have too little friction and the differential air pressures just pop out the brakes?
Is this for air brakes? Because you did mention air brakes. Okay.
The tabs pop out.
Oh, the tabs popping out.
Yep.
So one thing that we can do to prevent this is itself using that safety mechanism that we have, hitting the apogee, we can send a signal to close this, have it retracted, because the air brakes itself, the servo motor will be completely retracted to its neutral position, as of so. And we can also take advantage of our safety mechanism to be actuated and holding them all in place. If that's answers the question.
Yeah, I think that you've had a look at the limit load that would be required to effectively break that safety mechanism.
That Charlie has asked for that.
The safety mechanism is in its preliminary stages. We were looking at a different configuration up until recently, so there is still a lot of work to be done on it. I have looked at the static friction loads, and the springs are capable of handling them. We will be doing extensive testing on their capability.
And the dynamic pressure difference, because you're not going to be, your maximum velocity is, well, you've still got quite a dense amount of atmosphere around you. So you're going to not have lost a lot of that pressure inside your vehicle, but as your slipstream will be at a much lower pressure. What's to stop early deployment because of the pressure differential?
That will need to be tested. We can calculate that. Just do you want me to hand this over to you?
Yeah, that's a really good question. It's just the fact that when we were choosing our servo motor, we intentionally chose a very high torque, so it's a 45 kilogram centimeter servo motor, which compared to last year, which was 25 kilogram centimeter. We have taken this into consideration, and we will have so that the movement of the shaft of the servo motor itself is very difficult to do so. That prevents all of this dynamic pressure difference. But as of just you mentioned, there hasn't been much work on that prevention of this. It was mostly focused on safety mechanism if the deployment fails to deploy back and retract, provided that it's a safety requirement by URC, and there's nothing on this specifically on when it's not actuating then to be deployed.
Cool, thank you. Another question, if you go back a slide or three, where you've got your actual control loop. There we go. I noticed you've got an altitude approximation using the Mach number. What sort of sensors for altitude and velocity do you have on board, or is this something that's going to be answered next by avionics?
Yeah, so we've got a carbon filter which is using sensor fusion from a barometer which does altitude, and we also have accelerometers and an IMU. So we should be able to use Kalman filtering, which uses somewhat like dead reckoning to be able to fill in the gaps in between each barometer reading to be able to see the height. And the IMU and accelerometer can refresh at a high enough rate that we don't have to worry about how quick that is. That will be always up to date.
Fantastic, thank you.
Yeah, so just on this slide, are you just doing like a one-dimensional analysis of the altitude performance, or are you doing 6-degree of freedom model?
So this is going to be on board a ESP32 or STM32-like computer. So we haven't had the opportunity to do performance testing on a fourth-order room footer extrapolation of the height. And depending on how that goes, we can look at potentially a three-dimensional model with 6 degrees of freedom. But for now, we're assuming that a perfectly vertical flight. And we think that there are going to be other factors which will be higher margin of error before that becomes an issue. Because the air brakes will operate immediately after the thruster stops. And so we're assuming that at that point, it will be basically straight, as long as the other teams can keep it straight with the with the fins. But that's something that we can look at in the future if we have enough time.
Since no one has a question, I just wanted to quickly go back to the hang on. This. Not expecting an answer now, but if people could have a think about it and maybe come to us during the break. But as I said before, we're not sure if we should do a pyro-pneumatic SRAD or a DC SRAD. And also, if we did an SRAD, we could have either two 38-gram canisters, because I think the preference is not to use that MDF disc that we have to, but we might have to use to increase the pressure. But the issue with that was that if we had two COTS canisters and then also our SRAD, and then also having the two E-matches for the tether device, I don't think avionics has enough ports for all of those. I believe they only have 4. So.
To be honest, I don't fully understand this trade-off. It's probably not time yet. But are you going to test each of these options before you make a decision? That would be one way to gain confidence.
Yeah, so one thing about both design is that on a normal basis, they are the same dimensions, so they share the same canister sizing, same thread sizing and all. The addition to the new pyro-pneumatic that we've got is a casing to the side of it that holds in place our DC motor. And so by adding the slots available on the device itself, it will enable us to place our disc inside to have
just in the interest of time, I don't think I'm going to understand it from your verbal explanation. I think more diagrams would be needed. Just, are you going to do each one as a test program individually?
There's the plan.
Before you make a decision? Yeah, I think that's probably right.
Is there any issues with using 2S rights instead of, and like if we did proficient testing and we did one of the pyro and one of the DC and the pyro is the backup, knowing that, because it has no difference to the costs other than the fact that we're getting a bigger canister.
I don't understand your system architecture.
Without knowing the program rules, I couldn't say, but there's the old sort of design philosophy that the best part is no part. Try and keep it as simple as you can. Fewer things to break.
Thank you.
We have like 5 minutes. Any other question? In your failure mode, you mentioned no recovery going off. Have you considered early recovery? So you haven't reached apogee and for some reason your recovery system deploys. How do you plan to account for that?
As of the so a safety thing, so as of previous experiences, there was always this high chance of having e-matches activated and having earlier stages of recovery, which it's a really good question for avionics, provided how do you aim to reduce this factor of not having this happening and preventing this, given that our system itself cannot be actuated or the pyro going off without electricity or a electrical charge bit in our images itself.
Yeah, avionics will run through this in a bit, but they have a state machine which will be running to ensure that things can't go off when they're not meant to. So that's how we deal with that.
Yeah, my question here, I noticed Sarah's question around timing of failure is quite interesting. Looking at subsystem or system design, quite like an FFA or a functional failure process that has keywords around too early, too late, wrong message, that type of stuff. Also, looking at your table here, maybe it's a broader question around your risk management. Why don't you break down your diagram decision flow? Is there a distinction made between consequence and likelihood in your risk management process? So, the combination of both of those actually gives you your risk as opposed to just a non-credible event.
So just to have this like a bit more clear, you were talking about our risk assessments and how to prevent this from happening.
It's more, are you doing it in a fashion that allows you to easily decide which risks you spend effort and time mitigating, as opposed to spending a large amount of effort and time on a very likely event? So so you can prioritize things that are high likely. You mentioned that this was the e-match thing, saying that this happens often. If that's something that happens often and it has catastrophic consequences, that should go to the top of your list.
So the way that we prioritize our risk assessment is based on the how flight critical this would be, and based on and also the e-matches being activated and charged. From my understanding, it has never happened in the history of ARD. We may have had some higher charges deployed, but not at a different expected time. And so most of our prioritizing our risk assessment comes from the ERC requirement itself, and also how flight critical it would be.
Hi, just to expand on the previous question. So within your logic flow that's running the air brakes, and this is sort of just a direct expansion. Do you have a active risk matrix that's running? So having prioritized risks before flight that's something you can engineer out and go through the engineering hierarchies to get rid of as far as you can. But as for the risks that you're actually experiencing in flight, you mentioned that e-matches haven't been an issue with ARD. I believe there's some individuals in the room that will be aware of issues that have happened in the past with other teams. Do you have any processes in place to have mitigations within the code to avoid early e-match detonation or other sort of avoidable functions that can be programmed?
Yeah, so absolutely. So we've got, I do the air brakes programming, so I can speak specifically to that. So a major failure point would be early deployment, in that we deploy our air brakes early or too much early on, and something like we don't get enough, we lose too much energy, we don't make our apogee that we want. So what we've got a safety factor on board, where essentially what we're doing is we have a multiplier of our absolute deployment amount, and we scale that between our expected altitude from when our thrusters turn off to near our altitude, our target altitude. And so we essentially make it impossible for it to fully deploy when immediately when we stop burning. So that number will go from maybe 0.6 to 1 as it reaches closer and closer to the target, and that ensures that we can't lose too much energy before we hit our target. And there's some talk of maybe doing only allowing the most extension at the very highest point, because that would mean we have way too much energy. But other systems can be mitigated. I'm sure that's something that avionics can talk about. They're a lot more on the deployment of the recovery system itself. Yeah, thank you.
All right, well done, guys. We have pizza incoming, so we're gonna take about a half an hour break to let everyone network a little bit. If you have any questions that came up, please feel free to talk to the rest of our team. And we will be right back with some food for everyone, and then we'll get into our avionics team. Thank you.
Do you have an option?
So Anna,
I mean, I love the scroll. This is a big deal.
Yeah, I know those, and that would be part of what's from an aerodynamics perspective. Not great. That would be. I would be. Whether they like
It'll help. You guys
where I
Sure.
Can you just show me the chart again for sorry, I think in terms of my capability to manufacture where I can help the most.
Sure. So we have. Are you talking about
The ground stations and payload. Okay, so aerostructures and sorry. There's nothing in terms of payload that I can add to it. And the things that really interested is making sure that you guys have like your manufacturing avenues.
Doing like another
diamond,
and you obviously have like a more
all the additive manufacturing at that point.
what are you including fiberglass?
Like if you need access to the cheap quote.
I mean, it's just like we built really large experiments and we had I wonder with it we had a wondering
that's kind of impressive that they have
Especially on the team. Like also, I think that is localized sections. Not really. It's actually
So there's different places. So there, they did the research. Yeah, but did the research. There are also
if they are like
whenever it comes to some
yeah, okay.
So we're just trying to make sure that we don't snap this.
Yeah.
Even if you have to, it might end up being the same as just the issue.
Yeah.
Does we have a normal way?
Yeah, I like the book. How
That's like
Oh yeah, yeah. We are I'm sure maybe a lot of some of it deserves as well. I would last year. I guess like I have like but then you gotta we have like we're not doing like a joint. We are doing like we're doing like where we everything we said is make sure like it's actually rolling things like that. Like just wanting to like conjunction pressures. We have to take action which like, but then like yeah, we get a couple of people like alright, give her a bunch of times. So we've got two. You can get back to the it's crazy. It's crazy. We have to also like initially sometimes like the act is good. It feels like we don't have enough time all the time. Yeah. So I love it. Yeah, pretty good.
I'm worried about I literally asked my like, if I was to go out, everything's more that's what it's on.
There are I want to get no, not really. But like I
What you can just read the cards, like I know.
Oh, what's cool next week? Yeah, I'm also going to yes, I was at the creation date doing
you miss like the
it's very nice. It won't get good. It's one yeah, I am. Yeah, I am pushing.
Especially like I actually
Also successful. Yeah, I think a lot of that. Yeah, I reckon a lot of that came down to like
User it does. It's not really. We gotta take care of freezer. Garage, probably down.
This sounds familiar. So they're actually just gonna apply for this random resume and then I say to have so
Yes. Did you guys get some pizza? No. Sure. That's all right. All good, all good. Yeah, our teammate was like, "Where are the Neomech guys? Like, let's go find." We saw you guys like walking like the other way. Like, oh my god, I hope you're not lost. And then, we apologize. No, that's all right. Yeah. Right, yeah. Pretty good. Yeah, I'm pretty happy. I always love it when we get grilled because it's exactly right. It's hard to get like the other members to grill each other, so you need like an external force to come in and just be like, have you thought about all this stuff? Students. So I'm in my final year now. So been part of ARD and Adept for 5 years now. At this point I'm like doing all the overarching stuff, and I try and grill them before industry does. See how that goes. I'm at Shoal currently. I'll likely be there next year. Yeah. No, but something's got to give. But this is just like it's like what other student can say like they've Thank you. I appreciate it. Definitely grill our teams. I know like a bunch of you guys are ex-error ones and like ex sort of everything. Yeah. So like just anything that comes to mind. Yeah. Well, speaking to Andy, I think we're gonna be working with you guys pretty closely. So if not now, I think a big part is just kind of sitting and like essentially being a sounding board with the team that's like with the manufacturing side, simulations with the FDA, especially FDA. Well, so for us, it's like it's technically not a requirement for the competition. We've done, it's we're on a very tight timeline. So last year we had like five projects. So we had these two. We've got a hybrid engine development that we're doing. We had two smaller rockets, and then we had a 2-stage rocket as well. And then all of our timelines got extended. And then once we did the competition, which was end of August, start of September, after that, like everyone was caught. So this year it's like we started later than we would like to. So some of those like simulation stuff we're behind on. So the idea is this year once we like we're
I guess like refining all of our processes. So then once the competition's done, we come back and by November, we're ready to start the next project cycle. So then we use the entire summer to do all of that CFD and things like that. But also a big thing is, I'd say a good 40% of our members, like senior members, graduated off. So most of the students you see here, they're all like first, second, third year with like zero CFD, like analysis experience. So it's like, all right, now we got to fill that like gap in knowledge. Yeah, so a few challenges there, but hopefully it all stabilizes by next year. Yeah. Sorry, I'm gonna get everyone back in, so we don't keep you guys here until like 11 p.m.
That'll be wait, how much is the current so what's like I have the option to control it. That was there are some limitations. So even if they're not mechanically linked, they could be if they're on mechanical they'll have the same amount potentially. Yeah. Issues with the is it used in other systems? So I use a lot of times. Some of them use something like that essentially has the whole back section they also work very well.
My legs are gonna be set.
It sounds like it's just fine.
Still
So how do you survive
Sure.
I mean,
Yeah. So when I
How do you obviously? No, shall I just? Oh. Why does the representative not control the? I have the. That's good. I like that. The thing is, how like. No, it's not. I mean, you want to come to my right, Heather? Where are you? You this slide. This slide. Yep. I don't know what it is.
And so because everyone's on.
I always have to.
Yes. No, right. At this point, yes, it's changed it all. No, not an issue at all. And then you got 15 minutes. You literally turn around.
Spike work?
Let's go. We're about.
It's going to get everyone. Let's wait till you see that.
I feel sorry for the guy who should experience it, but
You've got 3 slides.
Asking too much. I'll full budget.
Just stop talking and they'll come in.
Yeah, that's
all right, everyone. So my name is Hussein, and I am a team lead for the avionics subsystem. And this is my incredible team here. So the avionics subsystem, when it comes to model rocketry, essentially has 4 main functions. The first and most important, arguably, is deploying the rocket's recovery system. The second is actuating the air brake system, which flight systems spoke on earlier. The third is transmitting live data to a ground station. And the fourth is logging data locally for post-flight analysis. And essentially our scope this year as a team is to design SRAD, a student researched and designed avionics system. But one of the core requirements when it comes to the avionics system is dual redundancy. And the way that we achieve that is that we run a commercial off-the-shelf flight computer in parallel, particularly for the recovery system. And one of the questions that we might be asked is why we bother with an SRAD system when we can just have a COT system. And the answer for that is, firstly, SRAD avionics development is one of the core learning objectives of the team. And secondly, is that COT systems can handle the recovery system and like logging data, but having an SRAD system allows us to introduce advanced features like control of the air brakes and live telemetry with the ground station. So I'm going to hand it over to my team. Our team is divided into 3 subsystems: hardware, firmware, and the design of the avionics bay. And we'll explore all those different projects.
So I'll walk us through a basic hardware system overview. So our hardware consists of 3 boards. We've got a power board, telemetry board, and a flight computer board. So the power board interfaces with the batteries. We've got 3 18650 lithium-ion cells that come into that. We've got voltage regulators to bring it to the voltage that's needed by the boards, and the air brakes, and the battery connectors, and arming switches, so that we can arm it on the pad, which is a requirement of AULC. This feeds into the telemetry board, which contains a GPS module for recovery, a 915 megahertz LoRa transceiver, and two antennas to allow communication between that and our ground station. This receives data from the flight computer, which is sensors and main control unit, but it has a accelerometer, IMU, and barometer on board, which it uses Kalman filtering to resolve its sensor inputs, and that feeds into the state machine, which drives the recovery, air brakes, and that's that. So for our commercial off-the-shelf avionic system, we've got a Blue-Raven flight computer, which controls the parachute and recovery system, as well as a featherweight GPS module for dual redundant recovery. Also to the Callan to talk us through our powerboard.
Yeah, so with the powerboard, as mentioned, we've got three 18650s carrying the whole system. And so in total, that would give us about 11.1 volts, which can go a bit higher when fully charged and obviously go lower when it's running low in charge. And so the main objective is to split that into usable rails for all the other components. So we need 5 volts, that's meant to be 5 volts at the bottom with 3.3, and then 2 higher current rails for 7.4, and just a battery voltage rail. And so we're just using buck converters and voltage regulators to handle that. The other components we have is the switches, which we need 2 of those in series for dual redundancy. And then we've got our reverse polarity protection. That's to protect it if someone accidentally inserts the batteries in backwards and doesn't fry the whole system, which has been an issue in the past. So we've got that. And then also just a couple of fuses on the lower current rails, just in case there's an issue there. And then we've got a power budget on the bottom left. And we've kind of assumed 1 hour runtime, and that's only using about 17% of our total battery. So if need be, we could run the whole system for around about 6 hours. Yeah, next.
So we designed the flight computer board, which is mainly acts as a rocket's brain. Its main function is to control the deployment of the flight systems, which it does by obtaining data from the 3 sensors we implemented, the IMU, the barometer, and the accelerometer. It also logs data onto an AND flash. We also thought it would be useful to get audio confirmation when the rocket has been armed, which is why we put in an arming buzzer as well. And finally, it communicates with the telemetry board with the CAN transceiver.
So the MCU we chose, it has high performance and ample I2C, SPI, CAN, and PWM pins. The IMU we chose can measure up to 16G acceleration and 2000 DPS rotation. We also have a barometer, which can measure up to 3 to 12 kilopascals of pressure, which we use for altitude. And finally, we've added an additional accelerometer with up to 100 G of acceleration, just because this is more suitable for the rocket speeds and acceleration.
For integrating with flight systems, so for the air brake systems, the MCU sends a PWM signal to a server through a server connector.
And for the recovery, the MCU sends 2 signals. One is for an E-match sign, and the other is to a DC motor driving circuit, which unlocks a latch mechanism, which will unlock the gas canister, which was mentioned before.
So as mentioned earlier, the primary function of the telemetry board is to transmit real-time flight data from the flight computer and also GPS data to the ground station. The board transmits at 915 megahertz in the ISM band using a LoRa transceiver at 17 dBm. The onboard GPS receiver of the board transmits at a range from 1.5 to 1.6 gigahertz, which is far away enough from the LoRa transmission frequency to not cause any interference. And as mentioned earlier, the flight computer data is transmitted by CAN. A link budget was done as well, and the ground station can aim to receive at a power of just around minus 80 dBm, which gives plenty of headroom given the LoRa chip's high sensitivity. PCB is also using a custom 4-layer stack of using FR4 material, which is good for budget, and it should be ample for the performance given the frequency ranges. Also, we're including a dual redundant system using a COTS featherweight GPS tracker. And we've just looking for advice on how we can avoid interference between the COTS GPS tracker and our own LoRa transmission, because they run at very similar frequencies, and we're just looking for ideas on how we can work around that. Something we are looking at is that the individual bandwidths between those two frequencies can be separated, but we're just unsure about how that can be configured with the COTS featherweight GPS receiver. I'll pass it on to Kevin now, talking through the state machine.
Okay, yeah, so here is kind of our state machine. It's kind of like simple in that it goes from the first state to the second and the third and so forth, and you never like revisit a state which you visited previously. And yeah, so we have like some conditions that we have that we need to satisfy to go from like one state to another. And these are kind of just based off of like other people's public GitHub repositories which do similar things. So yeah, and some of them have like 2 or more, I guess, conditions that need to be met to go to the next state. And the idea with that is that if you have noisy data or something from your sensor, then hopefully it won't like accidentally go into the next state when it shouldn't.
So this year we're implementing sensor fusion as part of our system. So sensor fusion, for people who aren't aware, is basically taking data from several or multiple sensors and using them to create a much more accurate reading of the system. We've decided to use a Kalman filter for this, mainly because it's very well documented and just widely used. There's also some open source versions of it, which we can maybe fall back on and compare what we end up implementing. Yeah, next slide. Oh, thanks. So this is just like the vague idea of like a lot of times sensors, you know, they have lots of limitations to them. So for example, IMU has a lot lower limit to the G's it can read at compared to the high G accelerometer. So for example, our IMU would oversaturate out during the launch, and so we would, once we use readings from our high G accelerometer. So yep, go on. Okay, so this is kind of our plan at the moment. So we're going to implement the standard Kalman filter. The idea is to get a real like fundamental understanding of like how it works kind of thing. So doing like software in the loop, comparing that, testing it using like looking at the convergence of residuals, as well as comparing it to open rocket data, and then using flight data we have from the Blu-ray from last year's launch. Eventually we'll put it into the STM32 system and do some basic, well, after we've implemented that, we want to compare, see that it's been implemented the same as it has to our software side. So just a comparison to the same kind of verification and validation methods. And then we want to do some basic like sensor manipulation to look at how each sensor kind of works, and then eventually do a live test of it. The ultimate goal is to hopefully try and implement an extended Kalman filter. This is very complicated, so just kind of doing a very like piecemeal approach of like trying to reduce the complexity between steps.
So for this year's avionics bay, we've gone with 2 inner sleds. So these are going to be mounted vertically. So all the electronics will be housed on the outer side, except for one which will be on the inner. So, and the batteries for these COTS boards and the SRADs will be mounted horizontally, which will be 3D printed. So these boards will be acting as like, the trade's going to be acting as a structural base between the 2 vertical sleds, and the wiring is going to go from the batteries to the switches, which will be mounted on the side, and to the electronics. So this year, the estimated budget for the mass budget is approximately 1.6 to 1.8 kilograms.
So we've identified three main risks for our system, generally speaking. The first was that the inertial measurement unit, which is one of the sensors that we're using, saturates during the boost phase. And the way that we mitigated that was adding an additional high G accelerometer, which we would rely on during the boost phase before moving on to the IMU's data. The second is some sort of data loss failure between the telemetry board and the main flight computer. And essentially what we opted to do was to have a GPS model on our SRAT telemetry board so that it can keep operating independently and provide us with useful data even if we lose that data link. And the third was that our SRAT system completely fails. And this is a real possibility because SRAT systems are inherently unreliable, which is why we have that commercial off-the-shelf redundancy system to back it in case that happens. So moving forward, we have been in the schematic design phase over the past few months. So we have essentially finalized that, and post CDR, we plan on moving on to the detailed design of our PCB layouts for our SRAT boards. And then we'll have that manufactured, and then we'll do some sort of bring up testing. And essentially the plan is to have our electronics launched in a test flight before launching it in our main competition rocket. And the reason we want to do that is it would enable us to test our Kalman filter, test our flight computer. And what we do is, instead of having our SRAT system deploy the recovery system for that rocket, we'd have it sort of set software flags, and that would allow us to verify our system before we launch it on our competition rocket and have it actuate our recovery systems. So, yep, that's pretty much it.
And so the state machine, particularly the burnout detection, are you going to use the advanced sensor fusion based estimate of state, or are you going to just look at the basic filter of the accelerometer and reading?
So what tends to happen when you exit your thrust phase is that you have a big drop in acceleration, and you're very easily able to detect that because you get a massive drop in acceleration at that point. So we'll primarily be relying on our accelerometer for thrust detection.
Primarily or exclusively?
We haven't made that decision yet, but I presume, yeah, primarily.
I think the sensor fusion is great and good to do, but
yeah,
you have to be able to test it robustly, so you wouldn't want to rely on the output. That's something crucial in the state machine.
Yeah.
With your powertrain, you said they didn't have enough battery life for 6 hours, but an estimate time of flight of 1 hour. Why are we aiming for 17% battery usage as towards maybe 70% of battery usage with weight in mind?
So that's a good question. The reason we went with 18650s is they are batteries that we've used before. So another option would be to use LiPo pouches, and they would be the lighter option, but they're actually banned by the competition because of sort of safety concerns. So for us, 18650s are something that we've used in the past. We know that they're able to provide sufficient capacity. We know that they're able to provide the current that we're going to need, because we are going to have some high current events, particularly during some of the recovery deployment and air brake deployment, and all those different things. So it's a mix of being able to provide high current, being able to provide the capacity that we need, and also complying with the competition rules. Yeah.
Also, that the weight of the 18650 is barely, around 50 grams, maybe 60 or 70 grams each. So not very notable. And also, if we have 11.1 volts input, then we can just use boost buck converters, and yeah, current. We don't have to. Our cells probably won't be able to do 5 amps output reliably. So being able to drop that down makes it so we can be a bit more comfortable with that.
Got a couple of questions.
Yep.
I'll start with the ones about the radio link. In your link budget, haven't got what you think your link margin will be. So do you know what margin you're expecting to get from the link?
No, but in the link budget, I did use sort of worst case scenario numbers in calculating that. So I still think we've got plenty of headroom and shouldn't be a concern.
Yeah, okay. Yeah, it's probably a pretty important thing to think about because even just relying directly on the sensitivity numbers you get from the data sheet of Google, it's like the ground station receiver might not actually be realistic, especially if there's a lot of other transmitters using similar frequencies, which could be pretty likely.
Yeah, that's
close proximity, like another rocket using the same radio is going to be much closer than yours, driving you need your radio link to be working.
Yeah, that's definitely something. Yeah.
Another question is, in the link budget, what sort of antenna, like pointing blocks?
That's something I've been meaning to discuss with ground station. It's sort of, I'm actually unsure, but in terms of antenna gain, I sort of haven't really considered that it's going to be that high either.
So what is the antenna?
I think ground station is using a Yagi antenna.
On the satellite.
I haven't just so
it'll probably be a simple dipole antenna that we'll use in flight.
Okay, so what antenna?
I think the assumption that I saw was 2 dB.
Yeah, 2 dBi.
Yeah, so that's probably worth some more thought as well, because that's like the maximum gain of the dipole antenna.
Yeah,
especially when when it's on the launch pad, that's going to be pointing right at your ground station, and everything's going to be hunky dory.
Yeah.
But as soon as you get up, you're going to be like right in the null of that antenna.
Yeah, definitely.
So it might actually be worth considering. Well, I'm assuming the antenna orientation, but I'm not going to fix that just by changing the antenna orientation.
Yeah. It's definitely something that we haven't put much thought into yet. Yeah.
It's okay.
Might be it's a combination one for your sensors, your sensor fusion. You mentioned in your state machine that you're going to be doing a whole bunch of looking at a whole bunch of different sensors. Now, in a perfect world, you'd be able to look at them all the time. But well, it's far from perfect, and you have to follow your sensors at a certain frequency. What are your thoughts at this point of going through your various sensors and pulling your sensor readings so that it can feed into your sensor fusion algorithm and then this state machine, so you make sure that you're looking at the right sensors at the right rate at the right time?
So I'm not sure I completely understood your question. So I mean,
okay, that's cool. As an example, thruster clock. You're saying it's a suggested transition, 10 meters above the starting altitude and acceleration straight from 2G. So that is 2 separate sensors.
Yep.
Possibly 3 if you're doing your IMU and your accelerometers. How often are you going to be looking at those sensors as well as your tilt sensors and your rotation rate sensors?
Yep. So obviously each sensor will have sort of a different data rate. So for an example, a barometer would be much slower than your IMU. So we use something called like interrupt-driven timing, where we set sort of the sensor's data rate internally, and then whenever like a new reading is ready, we essentially like use an interrupt to take in that reading. But particularly when it comes to the state machine, the reason we want to look at different sensors before sort of transitioning between different states is that, and that this is some sort of a key concern for ours, particularly when it comes to sort of measuring apogee, for example. If one of our sensors gives us an incorrect reading and we are like completely dependent on that one sensor, that could have catastrophic consequences. So like one of the ways that we want to get around that is to be able to verify that state across different sensors. So like as an example, we pull our barometer and make sure that that barometer is giving us sort of a zero or a negative velocity reading, for example, as well as pulling our IMU and, for example, looking at like our gyro data, looking at how much the rocket is tilted. So if we are completely dependent on one condition, that could be an issue. But if we can verify that across multiple sensors, then our safety sort of margin is much bigger.
Yep, fair. The next question on that one would be control lag is probably the wrong term, but state lag. So you've got you've got burnt out, code teams going still really quite fast in up, and the aerodynamic drag is of course on the fins, so it's still going to be quite vertical. As it gets up towards apogee, it's going to get a little bit less stable, it's going to get a bit tilty, it's going to get a bit wobbly, and that's okay. At some point, it's going to turn over. That point might be after it's past apogee. So, for your control algorithm, have you thought about any sort of an attempt at predicting, looking at what the state is currently at, knowing that the state for some of the sensors will be lagging not just on the rate at which you're pulling those sensors, but physically, the state of the rocket physically lags the state you're trying to match.
The signals are generated too late.
Yeah, yeah.
I mean, we haven't we're not that far in terms of our implementation to definitely that's stuff we're considering, and like we want to do in the implementation there's a lot of steps so that we can kind of make sure we get kind of what we want. We're not just jumping to something and then Hail Mary it works on the actual live test. So that's kind of.
And by the way, having that sort of run through of that's a great idea, I haven't thought of that, or yeah, we're working on that one, or we haven't implemented that. It's perfectly fine. This is CDR after all.
The GPS approach, you've got the redundant GPS off the shelf thing. I didn't quite understand what the primary GPS was. Is that on the avionics board or the telemetry board?
So that would be on the telemetry board, the SRAD telemetry board. That would be our primary. That wouldn't just relay GPS data. It would also relay data from our IMU, from our barometer, and it would deploy. It would relay all of that data to a ground station. Whereas the COTS GPS tracker will just relay the sort of the GPS coordinates.
Yeah, so that is called the primary GPS.
Yeah.
I didn't see it on your block diagrams. I missed them. Just.
I think that's the orange one at the top. That refers to the telemetry. Yep.
Okay. So, will that GPS need to have lock on the way up, or is it really only about recovery when the payload is coming down slowly?
So
you know that once you hit speed thresholds and high acceleration rates, you'll lose GPS lock.
Yeah. So it mainly needs to have, the main purpose of having a GPS model on the rocket is so that we're able to recover it once it's landed. Because of the wind and all these different factors, the rocket can end up very, very far horizontally from where you started off. If you don't have a GPS tracker, there's a high likelihood that you've lost your rocket.
Does the GPS feed into the carbon filter which is used for?
No, so the GPS does not. No.
Oh,
I'm going to ask a very simple question. I mean, you came forth last year. How much of this have you used for anyway? I mean, is it completely new design, or?
So the SRAD system is completely new. The commercial off-the-shelf components we've used extensively in the past. So we have used these two commercial off-the-shelf components, but the SRAD system is completely new. We have some designed SRAD systems in the past, but like this is a new system. Yeah.
I'm not sure I missed it, but have you given much consideration into arming the rocket and yeah, how do you do that? Maybe it's safe.
It wasn't shown very well on the, this is like preliminary CAD render, but the plan is to have pull-pin arming. So we will have pull-pin switches mounted on top of these battery racks. And the idea is that you drill holes into the rocket's airframe, and once you're on the pad, you pull those switches out, and so that arms your electronics.
Copy, and like you have multiple, I guess, mechanisms to arm it. Like I know I'm pretty sure from the rules you have like a dual stage.
Yeah. So you have more than one switch, like in series. Yeah.
And like this MOS bay is mounted fairly deep inside the rocket, from what I saw, from like the structure. Like so, have you given much consideration to, I guess, yeah, how you actually physically put the MOS bay inside the rocket and be able to, I guess, mount those or like integrate those arming pins and then be able to like pull them out like in a I guess safe way. Yeah, I know it's something that we had struggled with in the past for sure. So I want to make sure you're aware of it now.
Yeah, I think one of sort of the main lessons from last year was accessibility, where it was very hard to access our avionics bay. Like once we were out there in White Cliffs, you had to sort of disassemble all of these different parts to actually be able to get towards your bay. And there was a lot of issues for that because we still had to do some work on our electronics. So that was a key focus this year. I think sort of the aerostructures team could speak better on this than I can, but yeah, that was a key focus this year.
Yeah, for sure. It's definitely something that you need to work on, you know, in the world with aerostructures.
Yeah, no, it is definitely something that we've discussed extensively. Yeah.
I'm sure it does.
Just spotted something. How many batteries do you have?
So
earlier you said 380.
So yeah, so our SRAD system is powered by 318, like a 3S18650 pack.
Yeah.
But we also need to have additional batteries for the commercial off-the-shelf electronics. So the plan right now is to have two extra 18650 cells, so that they would each power each of these flight computers independently. Because the whole idea is that your system needs to be completely independent. Your clock system needs to be completely independent. That includes different batteries, different switches, different everything.
That clears that out. Thank you.
Yeah.
I'm going to ask a quick question. I've just got, it's about the reverse polarity protection.
Yep.
I'm just wondering if whether there's another way to solve the issue of connecting battery networks. Because you kind of added an additional component that isn't actually required during the flight or every spread. It's really just protecting against I'm curious if you come up with any ideas to solve that.
So, sort of reverse polarity protection is something that is not incredibly difficult to implement in your schematic, but it's something that can go very far. Well, the other way to get around it would be to have sort of a mechanical failsafe where your connector physically won't plug in if you plug it in the wrong way. But sort of based on the connectors that we've chosen, yeah, so
they're polarized.
Yeah.
So we're using the Molex connectors for pretty much all of our power systems. So they're polarized anyway. This is just an extra fail-safe because last year we had trouble with reverse polarity, and it's just a MOSFET, so we aren't really stressed about the extra component and the design work involved.
I think it has some time. If no one has any more questions,
Hello, our ground station. Oh wow, avionics, so many stuff. Alrighty, ground station. My name is Dimi. I'm the ground station lead of AID, and I have here with me today Adam and Vihan. So why do we need a ground station? A ground station is required to receive real-time data during the flight of the rocket. We'll be receiving altitude, velocity, altitude, and GPS. We are also kind of planning to make a software to be able to estimate where the rocket lands. If we have more time, we will actually finish that concept, and everything will be stored independently on the onboard flight computer. So why don't we just use a featherweight GPS like we did last year? It actually worked quite successfully. However, there are some aspects that we feel like we need to have. It has a closed firmware, so we cannot actually extend or modify. And in our ground station, we will have a live 3D visualization and the trajectory of the rocket in a map. As I mentioned again, landing prediction. And we also have full ownership. If something breaks, we can fix it ourselves. If we need to modify or, for example, put a different antenna, we can always change it and put a different antenna. And this is also the ground station what we're building right now. It has a scalable foundation, meaning in the future we can be able to transmit data to different sub-teams, actually have a live recording of the rocket, of its flight. And yeah, now some risks that we have will be located in White Cliffs, and it's a remote location. There's no mobile coverage, and there's lots of dust. So we are hoping to develop the software with no internet dependency. And regarding the dust and sand, we're gonna have a Pelican style case, and it's gonna be sealed, ensuring that it's dust resistant. In the consideration in terms of like the heat, because we're gonna have the electronics, the monitor, and other electronics, so that it doesn't heat up. We're gonna have a fan to be sure no heating happens inside the system. And because it's a remote location, we are nearly like 300 kilometers away from a local community, Broken Hill. We're gonna have as a primary, we're gonna have a power bank, and as a backup, a generator AC input. And regarding the RF interference, we're gonna still be using the featherweight as a dual redundancy, just to make sure that we still have the GPS working and that we still receive all the data that we need. Now, in terms of the entire cost, the overall budget for the entire build is around 750 to 910 Australian dollars. Some of the things we actually have, meaning that our budget for this year will be actually lower. The one thing that we actually need to purchase, the main thing is the RF system, which we require for the tracking antenna. The actual mission control box, we had two designs. We chose this design because we were able to get a good deal on a Pelican box, which looks like this. It's all included.
Use your imagination.
Use your imagination. It's a blue box.
A proper case.
A proper case. It normally costs $600. We were able to get it for $150. Big steal. And now Adam is going to be talking about the tracking antenna.
The image isn't a real thing, just for awareness. I put that up there. So
just for imagination.
Start thinking about the sort of logic. So anyone who's dealt with communications arrays. 10,000 feet is not a big deal. 915 megahertz can get you up to, it's been used in the past, up to 240 to 280,000 feet. And something that I miss is that we have a lot of wiggle room. So what this platform is intended to be is an experimental element that the team can, into the future, play with as they please. As the team's goals surround professionalization, a key element in Adelaide is communications. So this intends to be used as a tool, mostly for learning. I could put that antenna or something similar on a post in the general direction and it would be fine. But that's not a very good learning experience. So this platform will be made out of mostly T-slot aluminium with 2 degrees of freedom of bearing to allow us to adjust its location. Potentially, should the team decide to in the future allow for the active transmission of data if they choose to, as well as if the team decides to go towards space shots, which is a key area of growth in the rocketry community, it would be able to track a CubeSat should it please. This is leveraging off some experience that I've had professionally. As far as the design, it follows the translation of stepper gear through on a rotational basis, so it goes from worm gear through a few other mechanisms to deal with slack. The entire thing will be sealed appropriately to deal with dust. Anyone who's done any rural trips will know how painful Australia's environment can be for electronics. So it's modular design that should give the team a fair amount of flexibility in what they want to do in the future. Yeah.
Yeah, so with all of this work, we need somewhere to show it. So we have decided to make a dashboard, something like this. This is a proof of concept model, implemented design. We would get the altitude, velocity, attitude, and the pressure from the rocket itself, and the other values will be calculated at ground station, like the maximum velocity it reached or the maximum altitude it reached. And then we would also have a 3D map showcasing the live trajectory of the rocket. And this is mainly we are hoping that we can integrate it with the landing zone estimation tool that we are hoping to build in the future, as in like we have a plan to do it, but nothing is finalized on that part of the project yet. So this is how the data will flow through a system where we get the data from a COTS ground station, and we will have our own inference engine that checks for packet losses and formats the data that we need it. And then we would go ahead and display it on ground station, and we would also log it locally on ground station as well as on the rocket by avionics. And this is the future project we have. Like if times allow, this is what we hope to do, is to make a predictive recovery system where it shows a landing zone with decreasing degrees of freedom.
It was intentional, we swear. Make sure you're
on purpose. Yeah, so we plan on getting the Whitecliff weather data from their weather station, which will be openly available, and using that as the input and the data from the rocket as the input, and make some kind of model that will help us predict where our rocket will land. Any questions?
Just before we get into questions, I'm just going to expand on a few of these elements because I know that we've got a lot of simulation-related people in the room, and I'm sure they're curious. making 6-degree freedom models is tough. However, it is possible with a lot of effort. What this specific item is focusing on mostly surrounds in the final descent, as in 1,200 feet, give or take, once both parachutes have been deployed, localizing an envelope for where we should go look for it. Anyone who's experienced high altitude rocket launches knows that the recovery can take a long time if you can't find it and if you don't have an idea where it is. So the electronics team has stated that the GPS will be running for a long while afterwards, so we should be able to get a decent bearing where it is. This tool mostly sits in the experimental space to potentially allow the team to further look into simulations as they please in the future. Taking data from the local weather station is very useful. However, getting altitude data, we can take that from a variety of other sources around what's actually experienced in those environments. There is also an interest internal within the team to develop our own libraries of that data. White Cliffs is, for lack of a better word, in the middle of nowhere. If anyone's been out that far, there's nothing there. And there are some very big wind currents that occur out there. So I would less prefer to rely on data from the 80s collected by NASA for a lot of the CFD that's being done, and rather preferred on locally collected information. So that is a growth area, and this is what this tool is. Similar to the ground station, it's growth area and an area for the team to experiment as they please. Yeah.
Any questions?
Good work. I like the ideas and my cool pictures. And Southern Launch, we're very interested to employ you guys.
Yeah.
I
didn't want to say directly, but yes, there is an intent to make this team obviously employable. Southern Launch has a very
relevant
key stake.
So just in terms of the competition though, how important is all of this stuff? What if you have a total catastrophic failure of your electric case enclosed electronics? What happens to competitions?
So there's actually no requirements in terms of the ground station. There's no limitations that we actually have. So this is kind of more like a.
You can still win even if.
Yeah, we can still win. This is more like a additional feature that we have been exploring as a team.
And recovery. So if your recovery is delayed by a day or something like that, because you just can't find it, that's kind of a sort of like factor for the competition.
It depends if it's within the limits of the competition.
Yeah, I need to grade it. So you need to recover the item so that they can assess whether it's been damaged, because an undamaged item is considered success.
Okay.
As far as so the grading for the competition requires obviously it surrounds its altitude, so that will be collected and stored in several spaces. I believe there's 2 different spaces on the rockets where that information can be stored. If our system goes kaput, any data that we've collected is also stored locally, so we have a bit of redundancy there.
Where I'm going with the question is just like if your back antenna fails, do you have a backup option?
Yes, the featherweight. The featherweight GPS.
That's the transmit.
Featherweight has also ground
on it. Pick up those signals.
The featherweight has a.
There is
So
a bit more context. So the featherweight and blue random systems are commonly deployed as the sole solutions for lots of teams. They also run on the same frequencies. We will be receiving the same information. So this is just an extra step, just for the sake of it almost.
Any further questions?
I have a question, at least for our competent people in the room. We've identified that dust is obviously an issue, and anyone who's dealt with dust and communications arrays knows that that's a problem. Something that might be of interest in the future is exploring maybe developing a radome for this island. Obviously, that's a large piece of work, but just to get your mind thinking about how large of a growth area that the ground station can be. Obviously, southern launch is a potential employment opportunity for people in the team. At the same time, South Australia has lots of launch facilities across a whole bunch of organisations. Potentially, there might be an opportunity in the future to assist in similar sort of applications as we might look towards making composite components for these items. Just a thought. Okay. Yeah. Oh, wait, there's a question. Even though I'm blind, I can still see.
I have a question about the GPS receiver. I don't know if you guys are the right team to ask this question, but is the GPS receivers, most of them have a velocity and altitude limit? Because we can do this stuff. Is that going to be a problem for you guys?
Do you want to answer the question?
In my experience, no. 99.9% of the student-developed projects around the world that do rockets use COTS off-the-shelf GPS products that are not type controlled, because obviously they wouldn't be able to use that type control ones. So there was a joke floated around a long while ago around that question, that no, it shouldn't be an issue. And the same with high fidelity accelerometers and dealing with the G-forces. This system will not be going fast enough to cause any of those to carry on. So we should be good in that area.
Okay, I've got another quick one. Just wondering if the ground segment, like the RF ground segment, seems like it's pretty complicated with the like tracking antenna and there's probably some downsides to having a Yagi antenna that's more directional. Maybe it needs to be, especially if that exists. I'm wondering if, I asked about the link budget before, but one of the things that the link budget will show you is what antenna gain you need close the link, and potentially you might not need a Yagi antenna and you might not need a pointed antenna at all.
And you are entirely correct. No, you're absolutely correct. I did the link budget analysis about 3 months ago. I was considering the options. The purpose of having the Yagi is mostly for when we get to those larger altitudes, as I say, ambitiously and aspirationally, towards the 240, potentially 1,000 feet mark as a big ambition, to allow for those the smaller budget that we will have. I believe we've got, I think it was 80 dBm was the approximation that was put on the screen in avionics. I'm sorry, I missed that. I was outside. I think we should be fine there, if my numbers are still right from StatCom course 2 years ago. So yeah, it is entirely overkill, intentionally. Hello.
Start. Yeah. Alrighty. Hello. This is the payload team. We got Ross here, we got Ebony and Devinder here. And yeah, to remind everyone what a payload is. So
experiment. We're going to put it inside a CubeSat, and on our rocket, it's going to be within the nose cone segment. All right. So according to the AURC rules, this has to survive the flight. It has to be at least 2 kilograms, and it cannot affect the launch trajectory or recovery, and it cannot contain any hazardous substances or live animals. Alrighty. So obviously, we will be experimenting on varying G-loads conditions that affect water retention. All right, so in this, we will investigate the water distribution behavior in soil during the rocket flight, and we're going to evaluate how these changes may influence the future of plant growth and agricultural systems in sort of space environments. So from this, we created a hypothesis, and that was water retention will decrease during periods of maximum G-loading and distribute randomly during microgravity.
Right, so just to further justify this project, we believe that understanding how water behaves in the soil under altered gravity conditions is critical for the future of spaceflight. The ongoing Artemis missions show that the global focus is shifting slightly towards deeper space and long-term missions where nourishment of astronauts is a more pressing issue. And so understanding for us how water distribution in soil, which is the main factor affecting plant growth, understanding how that changes in these conditions, in both the microgravity condition and the high G-load condition, is incredibly important. Yeah, we'll move on.
So before we conducted any of our research, we did flight simulation in open rocket again. However, we approximated 2 seconds of microgravity near the apogee and about 10 Gs of force at the maximum for 2 to 3 seconds, proving that our payload will undergo the various G loadings for our experiment.
So we've just got the electronic flow chart here. We're using 2 capacitive soil sensors, and they have the ability to sense both intensity of water surrounding it, but also the surface coverage as a percentage, which is really helpful for us. And this is just connected to a nano with an SD card reader, which helps store all the data that we need. We'll be recording for about half an hour, and then a power bank, and this power bank provides ample power. Our power requirements are pretty minimal. So our configuration we've decided on is 2 of these capacitive sensors, which again can sense the surface area coverage. And we hypothesize that in the period of high G loading, we get greater coverage at the bottom of the moisture sensors as the water will be flowing down and draining through. And then this will essentially restore, this distribution will essentially restore during the microgravity section of flight. And this is just connected to the nano LSB and the power below it.
So here is a demonstration of how we've catted up the internal configuration and the CubeSat and housing. So basically it will work as we've sectioned off the main soil section with the sensors, and then the MC underneath, and then the power at the bottom of the payload. And then that will be securely bolted into the CubeSat frame, this is the CAD designs that we have already done in Inventor. And then we've designed a housing unit to securely hold the CubeSat during flight. So obviously we don't want to be doing a fiddly attachment of the CubeSat before launch. So this housing unit will be mounted directly to the rocket, and then we can easily slide the CubeSat in on launch day. And then this is another drawing of the internal layout and external configuration of the CubeSat with an updated external skeleton of the configuration with the different sections. Yes. And we also have calculated our power budget for our payload. We calculated about 0.175 watts for the nano and the 2 sensors. So a 10,000 amp power unit will be sufficient and provide 171 hours of runtime. But this is a very conservative estimate because we have plenty of room in our 2U CubeSat. So space was an issue last year, but now we have plenty of more room to add more batteries if required after testing.
Yeah, so going forward, of course, our actual experiment is in quite the preliminary stages. So I think one of the most important things that we do as a team is testing, whether that be preliminary and continuous. So that, of course, includes testing of the sensors themselves, so their parameters, what we can work with, whether they are capable of what we want them to do, and how compatible they are with the kind of programs and the electronics that we want to include in our system. Another good thing to know, of course, is how resistant the sensors and the electronics are to water damage in case, of course, planning for the worst possible scenario. Other than that, we obviously have the soil retention behavior that we need to test. That includes leaking of the soil, pressure testing, saturation testing, also determining a possible saturation level that the soil should be at prior to launch. Even just determining if that's actually really an important parameter that we need to consider to get the kind of data collection that we want. And so kind of building on that, we identified quite a few risks and tried to kind of mitigate them as much as possible. The most significant risk being biological leakage. So that just means leakage of the water, leakage of the soil. It'd be kind of funny if after all this, the whole thing fails just because some water touched the electronics. So that involves just making sure we have airtight seals, making sure that the system we use, or like the little box that we put the soil and water in, is all airtight and it's all doesn't let any leakage through. Another significant risk, of course, is the rail misalignment and jamming. We mentioned that, of course, our design of having the guide rails lets us to kind of more conveniently put the payload in and out of the rocket. So that gives us convenience on the actual competition deadline. But we don't want that to kind of backfire on us. So we have to make sure that we have a smooth finish of the guide rails and everything like that, and make sure it actually, works as we want it to. Other risks include structural failure, of course. So we can do testing on that pretty simply and stuff like that. Yeah. And so our timeline, we definitely want to kind of go forward as quickly as possible. So after we need to finalize our designs and everything, and after that, pretty quickly kind of procure everything that we need. And that includes the sensors, the electronics, everything like that. Hoping to kind of finish on schedule as quick as possible, because payload, of course, we need to integrate that with all the other subsystems. So making sure we have enough time to do all that. And so in addition to all the questions that you guys might have, because like I said, we're in the preliminary stages of our experiment, we did have quite a few questions as well. If you had any advice, if anyone had any experience with a kind of similar experiment. So we've underlined the kind of main ones in that, for instance, which sensor types are most reliable, or what actually constitutes a good scientific experiment in a context like this. And yeah, as you can see, quite a few questions there. So yeah.
Yeah. Any questions? One answer.
Any biologists in the team? In your space missions, there's often like a principal investigator and the scientists and so on. But that's cool. You're going to do a good payload for an engineering project. So just how is the soil retained at the top? The diagram seemed to indicate it was just open at the top and tested.
So it wasn't included in the model, but there is a cap with 2 slots that sits.
I see, yes.
And it's screwed in, the screw holes are bolted under, but they're just screwed in the full location. And additionally, there's also this top triangle square, which goes on top of that. And that soil will be completely enclosed, and there'll be just 2 gaps. And I'm assuming the tolerance will be quite small.
So the hermetic sealing is basically the cube with the top base not shown.
Yeah.
Also, yeah, cool. Yeah. And then in terms of like testing, looking at one of the final slides about the test. Keep going.
Again.
More. Yeah. Sorry. So we've got testing of soil sensors and software development and component integration. What you don't have is like full payload integrated testing. That's probably
like inside the rocket, or how and or when are you planning on putting your payload together and verifying that you're getting answers that make sense without just sitting there on a bench, and then do something to it to try and replicate, even at some scale, what you expect to see during flight, so that you can see if you can measure any changes.
So yeah, so like run a test on the ground before you send it up, sort of thing.
Yeah.
I guess after we assemble the entire unit is when we can start testing. That's actually not true. We can start testing with just the soil cube, and just some on the table testing, but motion testing will have to come after the whole unit's assembled. That would definitely be something we will consider. Yeah.
Well, just in terms of questions to us, I kind of have a suggestion for one of them. What would be considered a strong ground control experiment? So, if you just leave it still in 1D, you should see some gravitational effect on the water. If you gradually rotate it about 3 different axes, you'll get a sort of time average gravity vector, and that should be roughly equivalent to what you see in zero gravity.
Yeah, just you have it there for 5 minutes, and then there for 5 minutes, and then there for 5 minutes. Yeah.
There's actually a name for that product that does that.
Yeah. But in terms of testing for the sensors, you just need to saturate the soil to get them out, because that's all the gravity's going to do is change the saturation level in the soil. So you've got lots of time to do those experiments before you get to full integration. At least you'll then know your sensitivity, potential, and you can then test it with tools beforehand to get one that shows.
Yeah, I think it's pretty easy to do lots of testing on this experiment, which would make it good.
Thanks, sir. Thanks.
Yes, thank you.
Anything else?
In terms of the soil to recommend, possibly one with a decent amount of organic carbon in it. From memory, the soil that they used to build out the Adelaide Oval so they could grow good grass for cricket comes from out Accleston way. So if you want to have a field trip out into the suburbs, go and liberate some soil from different parts of that part of the Torrens.
You're doing that stuff today. You're not trying to sell off some soil.
No, I moved to Clenting about 7 years ago. Lovely part of the
Is
world.
this just a follow up? Is there any the high carbon concentration affect water flow whatsoever?
From memory, and you want to talk to some soil scientists, like go down to Plants for Space. They'd be all over this one. Go grab yourself a PI. But from memory, organic carbon in the soil helps with water retention. So that can help with remediation of degraded farming lands. There's a couple of farmers movements where they're trying to get people to just grow weeds near watercourses to help slow down the speed of water through the watercourse and help to regrow vegetation out into semi-arid parts of land that have just been cut there because the idea was more grass means more cows, so we need more grass. Turns out you have an entire ecosystem. The ecosystem can support more grass, and then you can support more cow.
What do you think about
Cool. Any other questions?
Yeah, I've got one not related to the experiment itself, but the recording and analysis of it. I think you said earlier you're using a micro SD card to record all the data that you gather over the flight. They somewhat infamously, the parachutes don't work and they hit the ground. They have a tendency to shoot up and be quite unrecoverable to get the data off them. So have you considered maybe some padding around the slot or a second redundancy or potentially even telemetry live to the ground base so you can analyze it even if you can't recover the rocket?
Yeah, 100%. That's a very good point. So of course we will, when we actually put our payload together, we will add kind of a lot of puffing around to kind of make sure that, and that takes a lot of we'll talk to ground station as well. That's a great thing that we probably should think more about. Seeing if we can kind of have those readings available to us if they seem others better. Yeah.
We definitely have the space allowance for that as well. So
Just a suggestion if we want to simulate something like what we've experienced in IG, stick it on a string. You go well.
Yeah. Yeah.
It did a good job of these sort of proving locally concept.
Yeah. With it,
sort of how effective it are. I believe someone mentioned about the specific name for that filtering. Cool.
Yes.
Yes, what was it?
Sorry, I've been doing a lot of work with Plants and Space, Plants for Space. You want to get in touch with Maddie Parks and it's a thermostat. They have a gorgeous little design that you can build in nothing flat.
Plus Maddie's really cool. So yeah. Another wacky one out of left field. If you look at the biosecurity regulations about taking soil samples in New South Wales, because there's various restrictions about taking soil on or off places like vineyards and orchards. You might want to have a look about randomly bringing soil around because of various soil fungi and pests and the like.
There is a quarantine station on the way there, which might,
It's one I'm thinking out near Paringa, near Remba. They generally keep an eye on people going into the Riverland rather than heading out towards that little corner of Victoria on your way to Mildura. But yeah, it's security thing to have to think about.
As I recall, I think they had more concern with like bananas.
Oh yeah, definitely. But heading into the Riverland, that's the important thing to care about. Heading out into Victoria, well, that's somebody else's state.
Thank you.
Any other questions?
Thank you very much.
Thank you guys for
Awesome. Well done, everyone. I think that's a record for our team for timekeeping. We're actually 10 minutes under time, so well done. I just wanted to say a absolutely massive thank you to all of you guys from industry and academia who have joined us today. Really, you guys and your questions and your grilling for our team is what makes our projects possible. I think a lot of the people, I've mentioned it to a few people, a lot of our senior members graduated off last year. So most of the team that presented today, this was their first critical design review. So I think definitely they learned a lot, thrown straight into the deep end. So big round of applause for everyone. Yeah, so that really marks the end of our event. So thank you for joining us till so late on your Thursday night. Please, we do have some basic handouts as well. We've got some prospectuses as well. We're always looking for more support, whether it's coming to these, which you're already doing, but whether you have a particular interest in one of our sub teams and you want to come down to a couple of our meetings, whether it's supporting us with a little bit more funding, anything like that, we're always looking for. Yeah. Feel free to talk and amongst yourselves and network with our team a little bit more. But otherwise, our next event will hopefully be the unveiling of Project Kronos. So keep your eyes out for that. But yeah, thank you so much. Huh?